Now, let us discuss some mathematical detail of the wave motion. In this figure, show the path of wave on a string moving to the right. Okay, this path of wave moves to the right, and at t equal to 0, the wave is at this position. Okay, and if we take a snapshot of the wave at t equal to 0, we can explain, or we can describe the curve of the path as a function of the position x as y equal to fx. This function represents the shape of the path at t equal to 0. Now, when the wave path moves to the right, after the first snapshot here and the time pass as t here, if the velocity of the wave of the path is v, so the distance that the path moves is vt. Okay. Let us assume here that the shape of the path remains unchanged. It means that it's not changed in time. Okay, so it means that the whole path moves to the right without distortion. The functional form, the mathematical or the functional form of the curve of the path remain the same at the time t equal to 0, or at the time t here. But the location of the curve change in time. If the path moves with the velocity v, okay, you can see that if we look at the top of the path at this position will move with a distance vt when the time change from t equal to 0 to this time t. Okay, and also every point on the path move with the distance vt too. So it means that if we look at the point p at time t equal to 0 here, later at time t, the point this blue point about this point, which is at the distance vt from point p, will move to the position of point p, and it means that the medium, which is the string here at point p, is lift up to this position. Okay, so it means that at t equal to 0, the displacement of the medium at this point, the displacement of the medium at this point this is at t equal to 0, is equal to the displacement at the point P at time t. As I mentioned that the functional form of the wave remain the same at time t equal to 0 and at time t. So what we can say is that if we denote this position as x, this position as x, and if we denote this position as x prime, we can say that let's change the notation a little bit. Let's change this into the x0 and this as just x. From this figure you can see that x is equal to x0 plus vt. Okay, x is equal to x0 plus vt, or x0 equal to x minus vt. Okay, and you can see that at t equal to 0, at t equal to 0, the displacement of the pulp, this displacement is equal to x0. So we can say that y this y this displacement y is equal to f x0. This is at time t equal to 0. F represents the functional form of the pulp, represent the functional form of the pulp. Now, if we look at time t and we look at the same displacement of the string, you can see that if you look at the same displacement of the string y, we must have that at time t the same value of y equal to the f of x0, right? Because we look at the same displacement of the pulp just at this point P. Okay, so we still have y equal to f x0, but we can also write this as f of x minus vt, because we know the relation between x0 and x. X is the position of the that have the displacement equal to y at time t. So we can see that this is the general form of the wave of the propagation of the disturbance of the wave in one dimension. At any time t, you can write the wave function. We call this the shape of the wave. This function f as a wave function. And once we know the wave function, we can say that the displacement of the wave can be written as the f of x minus vt. This is for the wave that moves to the right or to the positive x-axis. You can see that if we put t equal to 0 here, x is equal to x0 for the displacement y. So we have at t equal to 0, y is equal to fx0. But when t increase, the pulse move to the right. Okay, the pulse move to the right, and the position with the same displacement y, this displacement move to the right also. So the value of f increase. The value of x increase. But when you subtract this with vt, we will get back to the value of x0, right? From this relation, we will go back to the value of x0, and when you put it to the wave function, it will give you the same displacement of the medium. So it means that if we look at a position on the wave, like if we look at this point and we follow the motion of this point when the wave moves to the right, we can explain the displacement of this point as a function y equal to f of x minus vt. But y is arbitrary. It means that we can observe any point on the wave. So it means that we can use this equation to describe the traveling wave or the wave that moves to the right. Okay. So this is the general functional form of the traveling wave move to the right or to the have the direction of the positive x. Move to the right or move in the direction of positive x. And using the same idea, we can show that for the traveling wave move to the left or to the direction of the negative x, the wave function can be written as y is equal to the f x plus vt. This is a wave function for the wave that moves to the minus x, or it means that if this wave moves to the left, okay, if this wave moves to the left, we can use this functional form to describe the motion of the wave.